All right, so I want to talk about training GPT-2 model on a distributed GPU cluster. This is stuff that I learned from Andrej Karpathy. Here is the, close this. Here's the link to his video. It's 4 hours long. It's great. There's a lot of code in it. What I want to do here is to briefly give a no-code version of it and the actual implementation, the training of it. All right, so for training this, I'm going to use a remote server provided by Lambda Labs. So here's Lambda Labs. You can create an instance, and right now I have an instance that's running with 8 GPUs. This cost me about $10 an hour, but I don't suspect the training will last more than an hour. To create new instances, you can come here and pick the type of infrastructure. And you can see there are different pricing. What is neat about this is that you can attach persistent storage to these instances. And that's exactly what I've done. So I have a storage here called NanoGPT that's currently in use. In this storage, I hold the training data and some of the logs. And I found it quite handy to do the low compute stuff on a inexpensive instance, dump the data into this persistent storage, and then attach the storage to a high-performing instance so that when you spin up that expensive instance, you really use it for computation and not for data manipulation. Now I will talk more about that, but let's take a step back and talk about the training data. That would be the first step. The training data comes from Hugging Face's Fine Web educational data set. So this is the actual data. This is a text file. So there's a huge amount of text here. And let's take a look at this. So just one bit of data here. Updated March 2011, click here, download, print, blah, blah, blah. Honest, open, talk about feeling can help often. So you have all this data sitting on a remote server. So the first step here is going to be this. In data preparation, I'm going to access this Hugging Face data set under S3 Amazon blob storage, and then import it into my local machine, transform it into tokens, and then store the tokens as NumPy file formats on my own laptop's persistent storage. This is the first step. I've done that, and let me see if I can show you. So if you look at this directory here, these are my NumPy files, and each of them is just a huge array of integers, and each integer being a token. All right, so I got this part done, but if you remember, next step is going to be to transfer this data into that remote persistent storage. So let me see. So that's my next step. From my local machine, I'm going to get each of these NumPy files and then send them to that remote instance. So for this, I spin up a low-cost remote instance in the same region where you want to have your high-performing instance. And then there is this rsync command that I ran, and it just transfer the files into that remote storage. So let me show you the command that I ran here. One moment. Here's the command. Let me close this. So what I'm saying is that sync the data from this directory that's sitting on my laptop into this remote server for which I have SSH credentials. And then in that remote server, there is a subdirectory which is this. And this directory is actually my attached persistent storage. And long story short, it takes every file in this directory that I have here into corresponding folder in that remote instance. And you can see it going through every file doing it. This took me somewhere between half an hour and 1 hour. And then I turned off or terminated the instance. Right. So that was this part. And at the end of this, you end up with persistent storage that contains a replica of all those NumPy files. So that is your training data. And now you want to do the actual training. So before you do the actual training, you have to transfer the code as well, which is quite trivial here. So on your local machine, you write the code, you push it to your GitHub repository, such that on that remote instance, you do a git pull and import all the codes on your instance. So in final state, on your remote instance, you're going to have all the data and the code. So here's what it looks like. Let me show you. All right, I'm gonna close this. Okay, here it is. So the first thing is that I did my cursor ideally. I SSH'd into the remote instance that is here. So this remote instance is running. Here's the SSH login. And once I'm there, I did a git clone and put my code here. And also I have my persistent storage with all the files, NumPy files in here. And now I'm training the model. And training the model is essentially, let me see if I have a illustration of this. So I have 8 GPUs attached to it, and I want to utilize all 8 of them. Let's look at how we're going to do this. If you look at this schematics here, so you have the persistent storage. Actually, it's not. This is remote persistent storage attached to your instance. The instance has 8 GPUs. Here I'm just showing 2, but imagine there will be 6 others. And here's how we're going to train this. Each batch, according to GPT-2 paper, has 500,000 tokens in it. For different versions of the GPT-2, there are different sizes of batch, but the smaller one is 500. And that's too large to fit into a GPU. So here is what we're going to do in the process. If you think about a batch with that large number of tokens, we break it into a smaller batch. Let's call them micro batches, which is very manageable and small you can work with. The numbering here is not accurate, but this is 64 times the context window, which is 1024. Nevertheless, each batch breaks into smaller batches. And what you would do now is send the first micro batch to GPU1, the second one to GPU2, and then the third one back to GPU1, so on and so forth. Now, if you, in my case where I have 8 GPUs, you can imagine the picture getting larger, but what remains is that you send a micro batch to one GPU, and then you would skip 8 essentially for the next time around, and the micro batches in between go to the other GPUs. By doing this, you're making sure that each GPU is training the model on a piece of data that is unique to that GPU. The other thing I should mention is that when you start training this, the same exact model is going to be sent to each of these GPUs. So each GPU is going to have an identical replica of the model, and it's going to be trained on different pieces of data, right? And imagine one batch is complete, and by that I mean these micro batches, all of them go through the GPU and are trained. During this process, what's happening is that the gradients in the models at each GPU is being accumulated, because by every backward pass of the model on each micro batch, you are adding gradient, you're depositing gradient to what was already there. The final step, when you finish completing one batch, is that torch run, and in particular distributed data parallel, and that is a module in torch NN parallel. What it does is called all reduce, which looks at the values of each gradient among all of these GPUs and average them. And once it has the average, it will replace the current value of the gradient with that average value. That is a way of these separate GPUs contributing to the development of a single model. And also that's the way of each GPU knowing or getting information from the other GPUs as the training continues. I think that is a key part of this distributed training that was insightful to me. Otherwise, the training remains the same as having a single GPU. All right, so I stopped the training for about after maybe an hour, and the reason is I didn't want to pay more. So I'm going to show you the cost, and I will show you the output. So essentially, we were set out to, let me show you. We wanted to run max, 19,000 batches, and that would correspond to one full pass on the training data, or one epoch. And the way this training is laid out right now, after each 5,000 batches, it stores the model weights here into the model 5000.pt. And once I got that checkpoint, I stopped it. I didn't want to pay more. Let me see if I can show you the cost breakdown. So here you have the 8 GPU A100 80 gigabyte SXM instance, and that was like $11, less than 1 hour, but I thought that's good enough, because if I wanted to run it one full epoch, that would be probably maybe $30 or so. What's interesting here is that you could train this whole thing with less than $100. our training was a little slow right now because we did a lot of evaluations in between, which is actually a good idea to show you what I mean by that. So I wish I could. So I'm getting all these things popping up because I terminated the instance, and this is the SSH connection. But let me show you. So here you have different steps, their amount of loss, learning rate. What you see here is that you get 1.2 million tokens processed per second. That's quite crazy. And each batch takes about half a second or 0.4 second. And here is the loss that's been going down. What I was going to show you is, oh my God, if I could stop this. Here are some examples of the model's output at the 5,000 checkpoint, which is quite interesting. Let me show you what's happening there. So the prompt has been that, hello, I'm a language model. And then the rest has been generated by this model that we trained. And we did it multiple passes so you can see. So each GPU has been giving you how many samples? Maybe 4 samples per GPU. So rank is the GPU number. So GPU number 3, sample 0. I gave it, hello, I'm a language model, and it predicted, and I'm not. It's also true. It's the only group around the human body that makes the body do, or the other one. And I'm a language model, and this was a great success because it was used to talk about a lot of things. I find it quite amazing that this model, that is not too much code actually, written from scratch with $10 of investment, can talk in such good fluency. And I didn't even complete one epoch, but say here I'm a language model, and now I'm a computer model, and a lot of computer models. I know you guys. It's whatever. I guess it ends at that point. I'm a language model. You know what that means? It's great. It's the same. The same thing holds true for computers too. Yeah, I guess that's all I wanted to share here. Now, if I go to my storage, let me see if I can refresh it. Now, I will be able to access the train model because I checkpointed the weights in that storage. So when I go, if I create an instance and connect it to the storage, I can create a model, import the weights, and make inferences with it.